Hi everyone. Today I will be presenting my lab on projectile motion. The purpose of this lab was to compare two models of projectile motion for a tennis ball that I threw and tracked using tracker software. One model with only gravity acting and another with both gravity and air resistance or drag force. The fundamental physics principle is Newton's second law. The sum of forces equals mass times acceleration. Gravity always acts downward and air drag resists motion. For my short throw, the gravity-only model matched my experimental data better. Drag did not play a significant role within the flight time. Models and main physics ideas. In the gravity-only model, the only force from the surroundings is Earth's gravity, which is F equals mg. This produces the standard parabolic trajectory. In the gravity plus drag model, I also included air resistance force, which is F drag equals negative B times V, where B is a drag coefficient and V is the velocity. This force always opposes motion, slowing the ball down more quickly. The reason for using both models is to test whether drag is significant for a light tennis ball in a short throw. Which brings me to the design of the experiment. For my system, we have the tennis ball, and for my surroundings, we have Earth's, which is gravity, and the air, or drag force. The ball had a measured mass of 0.0297 kg that we measured. Its initial position was about 0.005 meters in the x direction and negative 0.011 meters in the y direction. I used tracker to mark the position frame by frame. The axis was aligned with my initial throw, which set the release of the height to be about 0 meters. Initial velocity came from tracker data and was used in the code as starting position. In these photos, we can see how I aligned my axes. I aligned it with the starting position of the ball and then set 1 meter equal to that distance that the meter stick had, which was placed against the wall nearly close to where the ball was thrown. And then I had 25 different places where I marked where the ball was at that point in time. For the coding, I built two models in Python, one with the drag set to 0 and one with the drag included. The code updates the position and velocity step by step using Newton's second law. The code simulates the ball's motion using physics equations. First, it sets the mass, gravity, and drag coefficient. Then it calculates the forces step by step in small time intervals. With drag set to 0, it produces a smooth gravity-only parabola. With drag included, it adds an extra air resistance force that slightly reduces the range. Finally, the code plots both models against my tracker data so we can compare experiment and theory. When I compared my coded models to the experimental trajectory from tracker, the gravity-only parabola matched the tracker data very well. The drag model from my code, on the other hand, predicted a shorter range and didn't line up with the measured path. This makes sense because my throw only lasted about a second, which isn't long enough for air resistance to have a strong effect. In a longer flight or with a lighter object, drag model would bend trajectory downward more and shorten the distance, but for a dense object like a tennis ball over a short throw, gravity alone is the dominant force. The measure curve with the drag looks a little wobbly, while the gravity-only model is a perfectly smooth parabola. That wobbliness doesn't come from physics, it's from measurement noise. Each point comes from clicking in tracker, so small errors in calibration or frame marking show up as zigzags. The computer model, by contrast, follows exact equations, so it looks perfectly smooth. Few sources of error in this experiment. First, the calibration axis and tracker wasn't perfectly aligned with the floor, which could shift the trajectory slightly. Second, there is a human clicking error when marking the ball frame by frame. Third, a drag coefficient B was estimated, so it's only approximate. These uncertainties may affect small details of the curve, but overall, the gravity-only model already matched the motion very well, showing gravity was the dominant force. In this experiment, the ball did not reach terminal velocity. Terminal velocity happens when the downward pull of gravity is exactly balanced by the air resistance, so the net force is 0. But since my throw only lasted a fraction of a second, there wasn't enough time for drag to build up and balance gravity. That's why the ball kept accelerating downward instead of leveling off. Now, if I had thrown the ball straight up with the same initial speed, the motion would look different. Without drag, the ball would rise until its upward velocity reached 0, then fall back down, taking longer overall compared to the sideways throw. With drag included, it wouldn't rise as high, and would actually come down a little faster because drag slows the ball going up and reduces its speed on the way down. This shows how drag affects both parts of motion, not just the fall. In summary, we modeled a tennis ball's motion with gravity only and with gravity plus air resistance. The experimental data showed that for this short throw, gravity alone was sufficient to explain the trajectory. Drag would become more important in longer or faster motions, but here it was negligible.